Good evening. Good morning. Is it still morning somewhere? It probably is. Hello, everybody. I'm Lily Hout. I'm your moderator for this session. I would like to remind everybody this session is being recorded. All attendees have been placed on mute, and we ask that if you have a question, you put it into the chat and make sure you send it to all participants. And what I'm going to do now, we are going to begin now. We're going to talk a little bit about our sponsors. Our sponsors for all of the GPDIS sessions are Anarch, Cubatech 3D, and Transmagic. We appreciate our sponsors and we thank them for their continued support of GPDIS. Our other sponsors are the GPDIS partners that put a lot of work and effort into this, and they are including Boeing, SimData, Elysium, Northrop Grumman, Parker, and of course Peters has joined us in the past years. A little bit of history about the GPDIS, if we could go. We were formed in 2009. In case you didn't know, GPDIS stands for Global Product Data Interoperability Summit. It took us a while to come up with that name, but it was fun. It was a consolidation of two conferences and possibly a third, but the two I know for sure were the Data Exchange and SOA Deep Dives. I've been on the team since 2006. I was running the SOA Deep Dives, and then I had the pleasure of joining this team and calling it the GPDIS. We do address integration technologies along with, the non-proprietary exchange of data. We are a communication hub for our industry, and our principle is to foster knowledge through exchange of ideas, solutions, and methods. We have been doing that successfully since 2009, and we continue to grow, and hopefully, we continue to have folks showing up and sponsoring our conference, our virtual conference this year. The theme this year, the great race of digital transformation. The question they ask is, how is your model-based enterprise today? We're going to explore digital transformation, what it really takes for us to fully achieve it within our companies. And using the great race as a metaphor, we wanted to explore the building blocks of the digital transformation and how interoperability will enable the information journey for the industry. Today, I would like to introduce you to our first speaker. His name is David Odendahl. He's a technical fellow in the production engineering organization from the Boeing Company. He has a wide range of experience in the field of the computerized numerical controls portion of the industry, and he's a contributor to the STEP-NC effort. If you have a conversation with him, he will unsurprisingly bring up the need to rethink the existing CAD/CAM to the shop floor data model, and that's important that the digital thread between the design, manufacturing, and quality be maintained. If you let him keep talking, he's eventually going to talk to you about sailing, and he'll probably invite you along. Today, David's going to be speaking about the data standards for manufacturing in 2020. At this time, I'd like to turn it over to David.
Hey, Lily, thanks a lot. Bill is yet to be on the boat. We'll fix that one of these days. So today, in a fun-filled online meeting, which we all are, looking forward to doing these, we're going to be talking about the background of discrete manufacturing, primarily focused on CNC processes, and talk about some of the problems and solutions and where we're going with the solutions, and then you're all going to be inspired towards the end of it to help participate in this, and then we'll entertain questions at the end. And again, the questions, we're going to take them in the chat window. If you just send the chat to everybody, that'll help. Vicki talked about me. Vicki talked about me. Lily talked about me, but I like to talk about me too. I get there on the block a few times. I actually was an electronics technician, a maintenance engineer, controls engineer, and moved over to the CAD/CAM side, and now I work in production engineering. It's been a really interesting journey over the past, almost 40 years, and I learned a lot and appreciate a lot of different things from different people. I try to give back to what I've done that people have taught me over the years by participating in the ISO Working Group 15 Step Manufacturing Group and also the OMAC Machine Tool Work Group. The picture on the right is my son Mark, who is a nerd for Facebook Virtual Reality Labs, and that's my daughter on the left, who's valiantly teaching special ed in a remote world. So get back and talking about the subject at hand. This is kind of how we thought about things for a really long time. We had a flow from design in CAD, through process development in CAD, through manufacturing in a CNC, then inspection on a CMM. It's really pretty simple. Communication was one direction. There are a lot of proprietary standards did exist and still do exist in this world. There's been some pretty significant efforts over the decades in coming up with common standards to make these transfers more robust and reliable and easier to implement. Early standards in the process development side was a piece of software called APT, Automatically Programmed Tool is what that TLA stands for. There's been various standards for how CNCs accept data, RS-274, RS-494, communication to CMM machines using DMIS. All these standards, you know, as you would expect, are based on the technology of the time. They're very file size dependent. That is, they're doing everything they could to squeeze that information into a small file size because we had real storage and transmission limitations, and consequently the structures were really pretty primitive. But it did work. It has worked for a really, really long time, and this is basically the world that most manufacturing lives in. If you've been attending other sessions in GPDIS, you can see there's lots of better charts out there that talk about the digital thread and define the digital thread and what it is. The key thing about this, in my primitive little chart here, is that all these different components are still there, but they need to communicate with one another. And they need to communicate with each other in a bidirectional way. And so as a result, the simple 3 one-way communication streams you had to have now becomes 6. And there's a lot more data and a lot more stuff going on, and so things really get complicated. Digital twin, digital thread is the buzzword. It's near the top of the hype cycle right now. Everyone's talking about it. They want digital twin, digital thread, and that's really great and exciting, but then what do you do with it? Well, if you want to do something with it, then you have to add extra capabilities. So we take this little chart right here and move on to say, let's add an optimizer. Let's add a process optimizer that can work between design and process development and manufacturing inspection, start to tie all this stuff together. Well, when you do that, then if you want to do that, then you just bot yourself up to 10 bidirectional threads, all of large amounts of information that need to get passed between these disparate systems back and forth to one another. And it becomes a really big mess really quickly. And then if you want to do something more, let's say you want to add resource management to it. That is, okay, I've got a CNC machine tool, or I want to manage my cutters. I want to track what's going on in my cutters. I want to look at my inspection processes and tie that in. Every time you add something to get this information, then you just really complicated your data transfer. And we're up to, I think, 13 now is the count. And what's interesting is that if you look at this, I mean, this is a pretty big mess, and if you look really carefully at the demonstrations and proposals and stuff that you see in this world, let's talk about maybe doing some resource management or optimizing, you'll find that they don't show a picture like this. They'll just show the connection between a CNC and resources, or the connection between a CNC and an optimizer. They won't show the whole mess because it's such a difficult thing to deal with if you're dealing with point solutions, that is, point-to-point, unique proprietary connections between all these different components. And so again, if you look carefully in these demonstrations, you'll see little workarounds to that. Like you'll say, okay, so they want to develop communications between a CNC and a resource, so they'll invent a JSON schema to do that, or an XML schema to do that, or heck, even worse, they'll do a comment separate variable file Excel spreadsheet way of communicating this information, which works, and it can work in an individual segment, but it really misses the fact that you've got all these other components and processes that need to have access to the same data, and you're going to find out that whatever schema that you invent is going to be found wanting in the future, and you just get this big, massive mess. And it's important if we're going to do stuff, if we're going to be successful with stuff, and again, we're at the top of the hype cycle, that we make it implementable. So the idea of having a standard data bus can really, really help simplify this and make it easier for us to deploy and to expand and be really flexible as far as what are the things that we can do in this new world where we have ubiquitous data floating from different component to different component. So in this particular case, instead of getting rid of this rat's nest up here, we go to what is essentially a data bus, where we have standard data that's able to bidirectionally communicate with an optimizer and with resources and with inspection and manufacturing and so on, using standard data that's been carefully architected to understand the data requirements, both for the immediate problem or what the future problems and challenges and requirements might be, and that data being in a more modern architecture that is less restricted by the storage limitations of the 1960s. This makes it capable, it makes it flexible, and most importantly, it makes it usable. Here's just another view, slightly different on this. It just shows the context that how you can display context using the standard data bus, using various non-proprietary standards, where we have, in this particular case, an inspection resource would have access to tolerancing requirements and have access to the manufacturing process and the model definition. There are all these different entities being able to share with one another. And again, this gets easy as long as, or easier as long as we're selling on what that data needs to look like, and as long as we've got a comprehensive suite of tools that we can put into a standard data bus that we can use to share this information. So fortunately on this, there's a lot of work that's been done in industry and in standards organizations and academia to put this standard data bus together. So now that I've completely convinced you that we need to do it this way, what I want to do is spend much of the rest of this presentation talking about the various components of this standard data bus that's available to us now, where they are, how they work, and what state they're in. The first one I want to talk about is STEP. And probably most people have heard about STEP. STEP is ubiquitous throughout design ubiquitous throughout design. It's actually technically STEP. When people talk about it, they say, give me a STEP file. What they're really saying is, give me an ISO 10303-242 file, which is defined as a managed model-based 3D engineering. Us folks that work in the STEP world are notoriously vague and careless when it comes to throwing around terms and talking about something as STEP. You can call it STEP, you could call it 10303-242, or maybe we'll call it AP 232. It's all over the place. We're really sloppy about how we describe it. But STEP is supported by most CAD systems for 3D model communication. I'm not aware of any modern full-function CAD systems that do not support STEP directly. STEP has capabilities that are combined with other STEP application protocols. It's basically a database of different standards that can all work together. In this particular case, STEP 10303-242 is a convergence of the capabilities of STEP 203 and STEP 214. There's a problem in the slide here. And it has additional capabilities that you wouldn't expect. It can support geometry as tessellated or triangles, or you can it can represent data as VREP geometry, that is explicit definitions of geometry. It can support kinematics. It has tools for working with three-dimensional electrical harnesses, three-dimensional piping, dimensioning and tolerancing are all covered and capable within STEP 242. Addition 2 of STEP 242 was approved by ISO just this year in a pre-COVID world, and what kind of changed in that was that the standard became more modular. That means it became easier to share different components of the standard with other parts of the STEP suite of tools. Makes it a little more efficient, or a lot more efficient, is how we can work with it. The tolerancing capabilities, or PMI capabilities, were enhanced as well. This is an interesting tool here that you can get free from our friends at NIST, and it goes through and it will analyze a STEP file, give you a 3D model of what the file description is. In this particular case, if you squint your eyes, you can look and see that the representations of the PMI or the tolerancing are all there. They're all computer readable. They're all human readable. It's all integrated together, and you can validate that data, and you can pass that data from process to process. Another thing that happened in edition 2 of STEP 242 is an improved composites definition. That is for laying down, for the definition of the sorts of composites we folks at Boeing use for building airplanes and people use for doing all sorts of different things. Kinematics capability was enhanced, and actually Step 242, Edition 2, has some capabilities to define processes. So at a very low level, a high level, you can get somewhat of a process definition can be in Step 242. Ubiquitous, all over the place, does a whole lot of stuff, really easy to use and easy to get at. Slightly less known, or significantly less known than Step 242, is Step 238. And again, I'm being sloppy with my terminology. Step 238 is ISO 10303-238, or Application Interpreted Model for Computerized Numerical Controllers. And you can see why we say Step 238. It's got a slang term for it known as Step NC. It's got a modern data structure, and it follows CNC manufacturing processes. High-level information like what is the part, what's the stock, what's the fixturing, what's the cutters. But also in it, you can see low-level process information is there. The cutter motion is there. Machine functions are there. Auxiliary functions are there. Again, if you squint your eyes and look, you can see this is actually a file that's being displayed in a viewer by a small company called Step Tools. And this displays graphically the content that's an AP238 file. You can see the fixture, you can see the part, you can see the cutter definition, you can see tolerancing information. On the left-hand side, you can see the process group. Boeing is produced, in 2018, we produced over 1 million parts using Step 238. And right now, its status is the second draft of Edition 2 is in review. Because these standards are synchronized or harmonized with one another, we had to wait for Edition 2 of 242 to get completed for us to do our Edition 2. And consequently, we were able to take all those advanced capabilities that we saw in Edition 2 of 242 and have access to it in 238, which is pretty cool. So 232 did new things and better things. So some of the key capabilities for Edition 2 are, again, we inherited that modular infrastructure and architecture that we discussed in 242. We added automated composites manufacturing capability. If you look at this machine up on the right-hand side, I believe that lays down stringers for the 777X wing. I'm not completely sure. If you look really carefully, you can see you have different reels of fiber or tape and a multi-headed tape that will go down and will lay composites material down on this mandrel. We had to make some changes to the schema of AP238 to manage the fact that we're handling 8 or 10 or 12 or however many rows of tape at the same time. We had to do some modifications to make that work in an efficient manner. And so that's additional capability that's in Edition 2 of 238. We also added 3D printing process definition. You know, 3D printing, when you're talking about complex parts, 3D printing is really more than just printing. A lot of people look at 3D printing, and certainly by its name, and they say, I have a 3D definition of a solid, and I'm going to press a button, and this 3D printer is going to spit it out. Well, that can work to a really, with really simple parts, but it's not so great when it comes to things that are complicated. There actually are process definitions that have to be defined. For example, if you're doing aluminum powdered laser sintering, usually what you'll find is that the laser will take an extra pass around the periphery of the part. They'll do all sorts of different things with different processing patterns, and the industry is starting now to open up to the fact that we have to have more information going to these 3D printers than just a 3D solid definition. And so since AP238 has these capabilities for developing toolpaths and cutter motions, we have expanded 238 in order to manage and work with 3D printing and defining specific processes that lets us do more complicated parts of the sorts that at least folks like Boeing are more interested in. And again, as I mentioned previously, 238 inherits the AP242 capabilities, including tolerancing and kinematic modeling, and we're playing with that. We expect Edition 2 of AP238. The final draft was issued for international review a couple of weeks ago. Expectation is that it should be approved by the end of the year. Here's another one. This is ISO 13399. It's a cutting tool information standard. It's not part of the STEP suite of tools. All the STEP stuff is 10303. This is ISO 13399. It's managed by a different working group within ISO. It's STEP-like. It uses some of the capabilities of STEP representations, but it is its own standard. And it's for defining cutting tools. It is the capability of defining tool components, such as, here's the tool of the cutter itself. Here's an insert. Here's an adapter. Here's another adapter. Here's a tool holder. And that capability can all be represented in ISO 13399, what the assembly itself is. But wait, there's more. So also what it'll do is it'll define a cutting tool assembly. That is, how do these particular components fit together, and what are the rules for doing that? And it has the capability of providing assembly instructions for the tool room, and then also instructions and rules and data for the CNC machine tool to be able to utilize and understand and compensate for the length of that cutter or the diameter of that cutter, for example. Additional capabilities of ISO 13399 is it will handle multi-function capabilities. That would be for a mill turn machine, wherein one particular tool body may have an insert that's being used for turning, and it may have another inserts or more inserts that are being used for milling itself. And when you think about it, these relationships can really get pretty complicated, and that's when 13399 can step in a neutral, non-proprietary way and help you define the components of the assembly and the assembly itself. Folks at 13399 also realized, though, that they needed more, that they needed to be able to do more than just define the tool components. They wanted to have 3D models of everything. They wanted to have 2D drawings because some places still use paper and light paper, and they wanted to be able to define the connection rules. What cutter can fit into what insert that can fit into what adapter that can fit into one type of a tool holder. So instead of taking 13399 and making 13399 really, really big, what they did is they came up with the generic tool catalog, or the GTC. And that GTC basically is a packaging method or a packaging definition that lets you take all these sorts of information. The drawing can be in DXF, for example. The 3D models can be in STEP or in something else. This product data is actually the 13399 data. You got all get packaged up so that basically you can ship or deliver everything you needed to know about your cutter to your supplier and to your end user and to whoever else is involved in using that particular cutter. In my little high-tech presentation here, which I stole, you can see a little tool classification chart on the end that, again, looks at the definitions of tools, and you can also see a packing slip, including with the provenance of the data, who created the data, what's in there, and when was it created. It was a really, really pretty handy thing and a standard way for you to be able to find out everything that you need to know about that cutter or that tool. And you think about it, that your purchasing people need to know this information, your supplier needs to know it, your the CNC machine tool needs to know it, your tool presetting lab needs to know it. And basically it's all this data in one place, in one defined format. A lot of people are using this. If you look at this chart that I show right here, this work was, the pioneers in this were Sandvik, Cormorant, and ISCAR. They're the first ones to do it. Kennametal, Mitsubishi, and I'm not sure who these guys are on the lower left-hand corner, Horn, I guess. If you go to their websites, you can go to their websites, and particularly Sandvik, Cormorant, and ISCAR, you can select any tool, any cutter assembly, press a button, and it will give you a ISO 13399 GTC that will include the 13399 file definition and all this stuff in a neutral way. And then you can take it and you can load it into your system. Well, what systems care about? Well, these folks here in the upper right-hand side are all entities that can accept and work with ISO 13399. So that way you can go from your supplier, get your 13399 package, and hand it off to your tooling management system. And these particular CAM suppliers also accept 13399. They're pretty big ones. we all participate in that and understand and see the value of it. Interestingly, Sandvik Cormorant has just bought CG Tech and Vericut. I find that very interesting. And so that'll be a closer relationship, I imagine, we'll have going on. And the lower right-hand corner are various end users who have adopted 13.399 as part of their production process. It's really pretty cool. So the last of the standards and things we're going to talk about as far as direct standards is something called QIF, or the Quality Information Framework. It was developed by DMSC. These are the folks that were the developers of DEMIS. You may remember a few slides ago when you were paying complete attention to what I was talking about and not doing anything else, where DEMIS or DMIS was an earlier way of communicating CMM instructions and I think results too. The folks at DMSC realized that they had to do something more modern, and so they invented QIF. QIF started out as an ANSI standard. It's been harvested by ISO as 23952, so you can get it through ISO. Getting it harvested by ISO means that it complies with ISO requirements, and it's another revenue to get it, and means that they're going to have a little more broad exposure. This harvesting took place, I believe, also in 2020, if not late 2019. See, 2020 wasn't all bad. We had some good things happen. It's modern. It's an XML-based schema. If you look at this chart here on the right-hand side, it has measurement plans, resources, rules, executions, results, and statistics can all be defined in there. It's pretty easy to work with. I did a demonstration a few months back using QIF. I had limited help from our friends at QIF doing it because I wanted to see how good their deployment packages were. They were quite good. They had development kits that are available for free. They're in Python, C#, and C++. I took their .NET C# class and I converted to Visual Basic. And I did my coding in Visual Basic because I could. Because again, it was part of the .NET infrastructure and it was really pretty easy to do. If anyone is looking at any tips or hints on the conversion to Visual Basic, you can feel free to contact me about it. And the DMSC website, which I have up here, I think they also got one called QIF. They also, again, they provide these development kits for free, and they're quite good. They're quite easy to use. So stay tuned because in 2 days on Thursday, Jennifer Heron, and Curtis Brown from DMSC are going to be spending a whole lot of time talking about QIF. And QIF's really interesting to me. I'm not really a QA person, but I've been working with QIF standards for a couple of years now and find it really powerful and really interesting. So I hope you stay tuned for that and you show up for that GPDIS session in 2 days. That button didn't work. Let's try another one. There we go. Yeah, I touched briefly on a demonstration that I did. We did this as part as the ISO meeting in Toulouse, France, back in May of last year, and I've kind of shopped it around Boeing a bit. And the point of the standard was, the point of the demonstration was to show that we could keep context of quality information and quality requirements throughout the entire PLM lifecycle. So what we did was we took this test part, which actually came from our friends at Airbus. We assigned the toleration requirements we assigned to the data. It was linked to the data itself. We then used STEP to manufacture the part. We then used that STEP file to go through and automatically generate a program for a CMM to probe and inspect that part. And then we then took that information that came from the inspection of the part, which happened to be in QIF. I imported it with this little tool that I created back into CAV5 so that essentially what you could do is that you could right-click on a tolerance. And so this, you can see this is highlighted right here. You could right-click on a tolerance, and what would pop up was a little crummy little SPC chart that I created that showed what the results of the past 20 runs on that part were. And this is all made possible by the use of UUIDs, and I believe they're going to be talking about UUIDs or QUIDs, I think they call them in QIF, same thing, and show how we're able to use these unique tags in order to keep the context and keep the relationship between a manufacturing process, an inspection process, a design tolerance, and the actual design feature itself all linked together, which lets us use the digital thread in order to do something really, really useful, which is like have the design engineers have a look at the part that they designed throughout the manufacturing process and see how well it did. And again, stay tuned next week for that. It's really, really cool, really, really exciting to me, but I'm a nerd. The last thing I want to talk about in the world of standards is what's not a standard in the common sense, but a framework. It's not enough to really just have all these standards and define this data standards bus that I talked about a few slides ago, right? We need to be careful to make sure that we've gone through and we've thought about how these pieces fit together. What ways make sense? What ways don't make sense? In such a way that we can learn from one another, not make the same mistakes other folks have and have a common language so we can communicate amongst one another. So working group 15, part of ICE, is the same working group that's in charge of STEP AP238, which we all know is also called STEP NC or AP238 to the people that are really in the know. We have ISO 23247, which is a digital twin framework for manufacturing. So a standard per se, but it's a framework. It doesn't tell you what standards you have to use. It doesn't tell you how you have to do things. It just describes a framework about how different standards can be used in order to be effective in doing digital twin manufacturing. And to talk about that a little bit more, here's another chart and a definition of it. It's divided into different levels. The bottom level of this is the observable manufacturing element, and that's basically keeping an eye on what happens to the actual equipment when it's doing manufacturing or inspecting. The data collection and device control entity collects that data, and typically what we've seen in the applications that we've been demonstrating, it also transfers from the proprietary world of proprietary data standards down here up into standard data upstream. It makes it a lot easier to work with, where we can use that data standards plus that we talked about. Well, that's interesting. That's the wrong button. There we go. The digital twin entity is the area where digital twin models are being kept. Keep in mind that you've all heard about digital twins. You could have a digital twin of a part, you could have a digital twin of a structure, but you could also have a digital twin of a process. And for us at Boeing, it's important for us to not only know that the structure was manufactured, but in what manner it was manufactured, that the process requirements are being followed as well. And then finally, at the top, learning and acting, that is the user entity level. Top talks about the information that we learned is able to harvest information from the digital twins so it can learn, develop understanding of what's going on in the manufacturing process and potentially optimize it. 23247 is layered on top of the IoT architecture, and it passed its second draft ballot, passed just a couple weeks ago, and we've got a meeting tomorrow at 5 o'clock in the morning to talk about responding to the comments that we got to the DIS ballot. Here's another view into this, the digital twin manufacturing framework. It shows a particular use case that we did where we had 4 robots that were working cooperatively together to drill holes in a simulated wing assembly. And so it's just another way of looking and architecting a system using the terminology and the framework and the concepts of of ISO 23247. About 2 weeks ago, what we did was, being manufacturing folks, we do everything that we can to keep grounded in the real world of the actual production world and the actual design world. And here's a link here too. We did a demonstration, again, a few weeks ago about 3 use cases using the ISO 23247 framework. The one on the left-hand side was one that was sponsored by Boeing. Again, it was what I discussed earlier, the flexible scheduling for robotic drill and fill. What we were able to do was we were able to automatically adjust what our manufacturing process was going to be based on the condition of the structure coming into the cell. This robot cell is at the University of Washington Boeing BARC lab in Seattle. A second use case that we did was process optimization. This created digital twins of the cutters and manufacturing processes. It was done by our friends at Sandvik Pomerant and Michitoyo. And we showed that we could create digital twins of cutters with a potential of doing a better job of predicting tool life. The last demonstration was on fastener length optimization on an F-35. In that particular case, we were drilling, virtually assembling the structure using digital twins and able to predict what the optimum fastener length was for this piece of structure, which they saw the potential of reducing weight on the aircraft by a couple hundred pounds, which is really pretty significant. We did this demo a few weeks ago. Again, it's available online. Digital twin, digital thread is really high in the hype cycle. We had over 300 viewers online participate in that conference. So we're really excited about that. There's a lot of people that are involved in this. There's a lot of people that are paying attention to it. And so now it's time for you to be inspired. I'd like to think that I made a good case that the standards make the complex relationships implementable. We just got to be really careful. It's easier for us to look at a single problem or more likely a small segment of a problem and develop a tool and something that's just a point solution from one end to another. And, you know, we've been doing that in manufacturing for decades, and it's worked. But at the same point, it really hasn't worked when it comes to scaling and talking about adding additional capabilities. If you look at this work that's been done by aerospace competitors and been done by different technology suppliers, we're not going to do this on our own. There is nobody out there that is an expert on all this stuff. And so as a result, we need to communicate with one another. Not only communicate with one another in standards and being able to pass data around back and forth to one another, but we need to be able to communicate with one another and talk with one another and participate in these broader infrastructure type efforts so that we can all benefit from them. We do have a lot of people working this, but we're not snobs. Opportunities are there to participate in shaping this work. Sometimes it takes a little more dedication. Like, for example, if we're having the meeting tomorrow, is going to have a lot of people in Europe, West Coast of the U.S., East Coast of Europe, Korea, and so we're having it at 5 in the morning, which is okay. We do have to make extra effort because we're in the international world, but there's lots of opportunities to exist. One of the reasons Boeing participates in stuff like this is we don't want to get left behind. We want to make sure that what's going on is stuff that's going to work for us. We've got a lot of momentum. This is a buzzword. This is the top of the hype cycle. We had 300 people show up to our webinar 2 weeks ago in our demonstration of the use cases. So let's take advantage of this momentum and try to build off of it. So now that everybody's inspired, it's time to entertain some questions. And Lily, I think you hopefully got some. We could go back to both pictures.
Great. Thank you, David. Thanks. I got you. Sorry about that. I was on mute. Okay, folks, if you have a question for David, you can please place it in the chat, and I can ask him for you. Okay. What do you think the hardest part of a transformation to twin manufacturing will be?
Well, that's a brilliant question. In fact, it bears nothing to do with a loaded question that I had set up with you in advance, Lily. Kind of weird how it's just like that one. So the technology's there, right? The capability is there to do it as far as the technology is concerned. We're ironing out some details, but the computing power is there, the storage capability is there. A lot of people have been working this and doing this for a long time. The hardest part of this is cultural, in that because we've had these silos of capabilities separated from one another for decades and decades and decades, our organizations are set up that way. We have a design group, we have a manufacturing group, we have a quality group, and they're used to having their own borders. They're used to having things the way they've always been. So if I go to my design people and I say, hey, I need you to spend an extra 5 hours on this part to add semantic tolerancing information to the part itself so that we can use it and make it everything easier downstream, they're going to say, where's my 5 hours? I need more budget to do this. And if I go down to the CMM people or the quality people and say, hey, you know, you don't have to do all this manual work now. I need my 20 hours of benefits back. They're going to chase me out with a pitchfork because they would like to keep their money and they'd like to keep their funding. So part of what this does is, what this involves, it involves getting us together to work together to break down those borders to make sure that people are being measured differently, in that the design engineer is being measured not just on what their design is and how well the design works, but how easy it is to manufacture and how easy it is to support it throughout the rest of the PLM lifecycle. The technology is there, the standards are there, but what's tough about this is breaking down those borders. And if you go back to that demonstration, one of the reasons I did this demonstration a few slides back was simply for that reason. Well, all these stupid things are here. But this demonstration I did right here is I show this to design engineers, I show it to the quality engineers, I show it to the manufacturing people. And for the most part, the scales fall from their eyes and they realize that we're all in this together, and that when we populate the digital thread, it means that we can share this information and we can make things easier for everybody. That's a brilliant question, Lily. Thank you.
The next question is, you've been at this for a while. Why is it taking so long?
Oh, that one sounds familiar too. I think, that's mostly, a lot of the answers to the first question really kind of support why it's taking so long. It's taking so long because we've just been so crazy successful with our existing paradigm, with our existing models. That second or third slide that I showed that shows really simple relationships between CAD and CAM, and CAM and CNC, and CNC and quality. It's simple, it's basic, it's work, it's the easy way to go. Everyone assumes that's how things should be. And so it really, really takes some time for people, again, to sit back and realize they need to look at this more broadly, and that we can't just do this a segment at a time if we want to really, really make a step change and improve. I've used step change and paradigm already, so that's it for my buzzword allowance for the day and for this presentation.
Okay, and I think this is going to be the last question. Where are these standards being implemented in production?
So production right now, as far as Step 238 is concerned, the only company that I'm aware of that's using it regularly in production is Boeing. And again, we made 1 million parts using Step 238 in Boeing in 2018. I would venture a guess that we used it to develop more manufacturing processes than all the rest of our processes put together in that time. 13399 again is being used. A couple of your major manufacturers, cutter manufacturers, Sandvik, Iscar, whatever, are all using it. You go to their website, their entire catalogs are on 13399. And as far as STEP is concerned, STEP is just used all over the place as far as 3D model exchange. It's something that's basically become a non-problem. When someone's got information in one CAD system, so I want to move it to another, they transfer using STEP. It's ubiquitous, it works, it's solid, it's become a non-problem. QAS has been around for a couple of years. I'm sure that our folks on Thursday will have more information about where the deployments are on that. And that's it for my questions.
Okay. Well, with the exception of, I know you want me to ask you, it's a cool boat. What kind is it?
It is a cool boat. It is a CS-36 Merlin. It's a kind of an oddball boat. It was built in 1987, 36 feet long. And here's an interesting thing about it, that the actual fiberglass structure of that boat is cored. That is, there's a layer of balsa wood in between the outside of the core and the inside, the outside fiberglass structure and the inside. And that's done there to keep the boat lighter and stiffer and stronger. And it actually makes the boat a little bit warmer in the cold Pacific Northwest weather. The actual sailing world, there's been sometimes we follow them. And one of the things that aerospace has followed sail manufacturers is that modern sails are actually laid down in carbon with load paths being defined and carbon fibers being used following that load path specifically. And sails, a lot of modern sails are not so much sewn together from cloth, but they're actually laid up on a mold and cooked and baked to their final form. It's really interesting, that the industries follow different industries. So that's kind of it for. Yeah, sorry, Lily, is there more?
That's it for, yeah.
So,
nope, that was the last one.
Yeah, so we finished a little early, which is okay. So at the top of the hour, what's going to be happening is that we're going to be having Steve Caravella from Siemens is going to be talking about exploiting an electrical system model to increase EWIS manufacturing profitability. Now, a lot of that's gibberish to me. I expect it won't be by the end of it. And so what we'll do is that we're going to go on break until the top of the hour. Consider, too, though, that after the second session happens, Thursday, I think, Lily, is it the last one of the GPDIS online sessions?
No.
No, we got
one
more happening after that. And again, Jennifer and Curtis are going to be talking about QIF, and they're going to know a whole lot more about it than I am. And then we're going to be talking about, from Eris, about end-to-end digital thread, including all ID, including 3ID. So we're just going to go idle for a while, and we will see you back at the top of the hour.
And David's presentation will be available on gpdisonline.com, and it's under the event history down below. And it will be a few days before the video gets there, but the PDF for the presentation should be out there in a couple days. Great. Thank you. We're going to take a short break. And do we have Steve Caravella?
Unless